Okay, so now we're going to go through, we're going to do some analysis. What we saw just a minute ago in part 3 is that if I was looking to figure out what should go on the x cubed, that there were different places where I might be able to pick up a coefficient on x cubed. So for instance, when n was equal to 1 and k was equal to 1, I had 1 choose 1 x cubed. But when n was equal to 2 and k was equal to 0, I had 2 choose 0 x cubed. And so I just have one coefficient on x to the m, but there were different n and k combinations that might lead to that coefficient. And that's what I need to analyze now. So what we're going to do is we're going to say, assume that we're lining up these variables. So x to the m equals x to the n plus k plus 1, where n is greater than or equal to 0, and k can be between 0 and n. So I don't know what n is. N could be anything, but I know that k has to be constrained between 0 and n. So let's look at the different possibilities. So I know that m is equal to n plus k plus 1. So one possibility is that k is equal to 0. And if that's the case, then what you see is that m is equal to n plus 1. So n is equal to m minus 1. And so in this case, what you actually see is that you're going to have, in this summation, you're going to have an m minus 1 choose 0 times x to the m term. Because remember, we're assuming, the only way we can get this is if we're dealing with an x to the m. Similarly, if k is equal to 1, then that means that m is equal to n plus 2. So n is equal to m minus 2. And taking this and this, I can see that I'm going to end up with an m minus 2 choose 1 x to the m term. So far I know that at least I have these x to the m terms. And this is going to continue when k is equal to 2. I now have m is equal to n plus 3. So n is equal to m minus 3. So I'm looking at an m minus 3 choose 2 x to the m. And this is going to continue until at the very end, in the most extreme end of the iterating variable, I have k equals n. So that means that m is equal to n plus n, which means that n is equal to m minus n. So let's think about whether or not we could even get to here. I'm looking at k being n. So does this make sense? It does, sure. I'm being silly. It makes sense. So n is equal to m minus n, k is equal to n. Sorry, this should be n plus 1. That's really important because it's n plus k plus 1. So k is equal to n, m is equal to n plus 1. So that means that n is equal to m minus n plus 1. So I have, at the very end, I'm going to have an m minus n plus 1 choose n x to the m term. So when I write it out this way, all of the different coefficients that I could get on x to the m can be expressed in this pattern. So in other words, on the one hand, I have this is f of m, the mth Fibonacci number. But on the other hand, I have all these different ways I could get x to the m when I wrote it this way. So I have m minus 1 choose 0, x to the m, plus m minus 2 choose 1, x to the m, plus, and I'm just collecting these horizontally, plus m minus 3 choose 2, x to the m plus dot dot dot, and the very last one we had was m minus n plus 1 choose n x to the m. So is there a way I can express this as a summation? Alright, I'd like for you to try to do it. See if you can rewrite this pattern in summation notation. It's going to be something starts and goes up to something, something choose something, x to the m.